In this chapter, there's a whole section on the naming of compounds. This is what we call nomenclature. I'm not going to lecture on the nomenclature rules. They're very clearly explained in the textbook. You can also go online and probably find 10,000 videos on YouTube that go over all of these rules as well. Okay? But even better than that, I made you my own video for you to watch if you need it, that also goes over all of these rules that you can read for yourself in the textbook. And in that video, there's also a couple of practice exercises in there to help you along. It's basically like a lecture, okay? So there's separate slides that you can print out that go along with that video. But the important thing is that you're on your own to learn that at your own pace. I'm not going to be spending lecture time on it, but I'm expecting everybody to have studied that and know that material. I'm going to talk about those names a lot. And of course, on the exam, you'll be expected to understand them as well. But these are the main types of compounds that you're going to be expected to know how to name, and all that material is there for you, but you're on your own for this one. Here, let's put that one in bright pink here. On your own.
In this video, we're going to cover the naming and writing of formulas for chemical compounds. You can find this information pretty much anywhere on the internet. It's also very clearly written in your textbook, so we're not going to be using lecture time to cover this material. I'm holding yourselves responsible for learning this on your own, but this little tutorial video should help you along with that as well. So let's go through a couple of definitions. Specifically, we're talking about nomenclature. That's what the naming and writing of formulas are. Well, it's the naming of the compounds. That's the nomenclature, which is the assignment of a correct and unambiguous name, so nomenclature name, to each chemical compound. And with that, we also have a chemical formula, which is a representation of the compound using chemical symbols, like you see on the periodic table, and numerical subscripts. So both of these together, right, these allow us to identify the number and type of element. So first of all, it gives us a name and also the number and type of element, or type of atoms really, each atom being of a particular element in a compound. And we'll have two naming systems. One will be for ionic compounds and one for covalent compounds. For ionic compounds, and we talked about this a little bit in lecture already. For example, we may have sodium chloride, NaCl. We would write that as sodium chloride, and you'll see why we call it chloride and not chlorine in a little bit. Now, the way this is describing the compound, it has one sodium ion, so Na plus, one sodium ion, and it has one chloride ion. And these form what we call an ion pair. So each ion pair has one sodium and one chloride ion. Now, in an ionic compound, right, this is what we would call the formula unit. And in the formula unit, the subscripts will show us the lowest integer ratio of the ions involved. So in this case, sodium and chloride, there's one of each ion. There's one sodium and there's one chloride, so we don't actually put the subscripts 1 if it's just one, and we would show that as just sodium chloride. For covalent compounds, they actually form molecules. These are discrete units. That's to be contrasted with the formula unit for an ionic compound. That's a formula unit. This is within a much larger crystalline array, right? Whereas the covalent compounds, they don't form crystalline arrays. We have discrete molecules, discrete units. And here the subscripts will show us what the ratio of atoms are in the molecule. All right, so they're related, but they are different depending on whether it's an ionic compound or a covalent compound. An example here for covalent, H2O, water. As you will learn in this tutorial, water is a common name. If we wanted to actually give this a particular unambiguous name for the nomenclature rules, we would call this dihydrogen monoxide. And we'll go over the rules for that later. But we can tell from the chemical formula, in this case the molecular formula, that each molecule of dihydrogen monoxide has 2 hydrogen atoms and 1 oxygen atom. Okay, let's focus now on ionic compounds. Ionic compounds are formed due to the electrostatic attraction that's formed between anions and cations. Remember, anions are negatively charged and cations are positively charged. Now, these are often formed when a nonmetal, such as chlorine's a nonmetal, chlorine, would tend to gain an electron or more electrons. In this case, chlorine would gain 1 electron and form the chloride ion, Cl-. And doing so, this is what we call being reduced. When you gain electrons, you become reduced. And that doesn't happen on its own. Where does it get the electron from? That happens at the expense of another substance losing an electron. That tends to be a metal. In this example, a metal from the left-hand side of the periodic table, let's take sodium. Sodium would tend to lose an electron if it can, and sodium, in doing so, becomes the sodium ion, sodium plus, and it gives off an electron. So we can represent both of those with separate reduction and oxidation reactions. If I were to treat this as a set of equations, we can, with the arrows being equal signs, we can see that the electron on both sides of the equation will cancel each other out, and we end up with sodium metal plus chlorine nonmetal goes to form the sodium ion plus the chloride ion. And as I mentioned in this definition, right, these ions that were formed due to the oxidation and reduction now have a plus charge and a minus charge. They will attract each other and form an ionic bond, sodium chloride. Now when you come up with naming ionic compounds and also coming up with the chemical formula, you first need to determine what charge the ions will be when they're formed. Now in this case I chose one where each one is forming a single minus or a single plus charge. That won't always be the case, and as we'll learn in lecture, you can easily determine for some elements what the charge will be by just looking at their position on the periodic table. It has to do with their valence number of electrons and how many they will either gain or lose to come up with a full octet in their outermost shell. So that's what we'll call the octet rule, and again we'll cover all that in more detail in lecture. So step one is you need to be able to determine what that charge is going to be on the ions. In the example I just showed you with sodium and chloride, it's just a +1 and a -1. Let me give you another example. Let's say we're going to make a compound with aluminum and sulfur. Let's say we mix those two together and we want to know what kind of ionic compound would we form. So first we need to determine what the charge state would be on aluminum and sulfur when they form ions. So you need to consult your periodic table. First look at aluminum. Aluminum is a group 3A element, right? That means it has 3 valence electrons in its outermost shell. And as we'll study in more detail in lecture, you'll find that if given the opportunity, aluminum will actually lose 3 electrons, if it can, to drop down to a full octet, in this case looking like the electron configuration of neon. It will lose 3 electrons, and in doing so will become a cation with 3 positive charges. So we can write this as aluminum, if it can, will want to lose 3 electrons, and it will become aluminum 3 plus 3 electrons. Now take a look at sulfur. Sulfur is in group 6A. It has 6 valence electrons. If it can, it actually will gain 2 electrons, again, if it can, to fill its octet in its current period and pick up the electron configuration of its nearest noble gas, which in this case would be argon. So aluminum, it's easier for aluminum to lose 3 than it is to pick up 5. And for sulfur, it's easier to just pick up 2 more than it is to lose those 6. Again, with the goal of being in its most stable electron configuration, that being of its nearest noble gas. And again, if you're confused by this, that means we either didn't get to it yet in lecture, or we covered it and you didn't quite understand it. So here's an opportunity now to go back to the textbook and study up on the octet rule and valence electrons. All right, so if I draw this half reaction for sulfur, right, sulfur, if it can, will pick up 2 electrons, right, and become the sulfide ion. I drew this improperly. The sulfide ion would be 2 minus. It's picked up 2 electrons, so it has an overall net 2 minus charge. All right, so now we've satisfied step 1. For properly determining what the chemical formula will be for this ionic compound, we need to make sure that rule 2 is satisfied. Rule 2 tells us that the ratios of the ions have to be net 0. Now with sodium and chloride, that was easy because one was a +1 and one was a -1. So they, when you put them together, they net out to 0. That's not going to be the case if we just take one aluminum ion and one sulfide ion. Aluminum ion has 3 plus charges and a sulfide ion only has 2 minus charges. So that doesn't equal 0. So there's 2 ways that you can do this. The first way is just take the lowest common multiple. In this case, 3 times 2 is 6. So we want them to all equal 6. So if we take the lowest common multiple, all right, that's going to be 6. So if we have 2 times 3 plus, that's going to give us 6 plus charges. And if we have 3 times 2 minus, that's going to give us 6 minus charges. 6 plus, 6 minus, that nets out to 0. Very convenient. So now we know that there are 2 of the aluminum ions and there are 3 of the sulfide ions. So Al2S3. And that would be the chemical formula. Now the other way to do it that students often learn is what we kind of call the crisscross method. Right? We take aluminum, we take the sulfur, and we know that the aluminum will form a 3 plus ion, and we know that the sulfur will form a 2 minus ion. So the crisscross simply means you take the number of charges on one, and that turns into the subscript on the other one. So the number of charges on aluminum is 3, so that turns into the subscript 3 on the other ion of the pair. So it's fine with me if you want to learn the crisscross method to do it, although I often don't like shortcuts without understanding what's going on underneath that shortcut. So to do that, you need to think about the lowest common multiple, making sure that the ratio of the ions give you overall a net 0 charge in the compound. Now I want you to notice in each of these cases for sodium chloride and for aluminum sulfide, I have very carefully written the cation first and the anion second. Right? That's part of our naming scheme. So for all of these, the cation is always listed first and the anion is always listed second. All right, so before we go any further, let's just practice a little bit with some of these. So we're going to take a look at these pair of elements and decide, 1, what kind of ions will they form, and then 2, in what ratios will they form so that overall the compound is a net neutral charge. Now in this case, the compound, it's the formula unit, because we don't have just one molecule of these compounds. It forms a large crystalline array. So the formula unit, which is the lowest integer ratio of the ions, that has to be 0. Okay, so the lowest integer ratio of ions have to be net 0. That's how you determine the lowest integer ratio, right? And of course, this is the formula unit. Okay, so if you take some sodium and you take some oxygen, well, you have to consult the periodic table and see where sodium is, right? Sodium, being in group 1, is going to lose 1 electron, so it will be sodium plus. Oxygen, being in group 6, is going to want to pick up 2 electrons, so oxygen would be 2 minus. So when you mix these two together, you need to have them be net zero. So if we use the lowest common multiple, that would be 1 times 2, that's 2. So we overall have to have 2 plus charges and 2 minus charges. So we already have 2 minus charges. That's if we just have 1 oxygen, 2 minus, that's going to equal 2 minus charges. If we have 2 sodium ions, each one being a plus charge, we'll have 2 plus, and now we have net zero. So now we know that the answer is sodium subscript 2 oxygen. And we would call this sodium oxide. Now if you want to do it the crisscross way, all right, you write the cation first, that's sodium, and the anion second, that's going to be oxygen. We know that the oxygen would have a 2 minus charge and the sodium would have a 1 plus charge. So the 1 goes down there, and we don't usually show the 1. And the 2 minus charges on the oxygen, that means that we have a 2 subscript down there. All right, how about lithium and bromine? Well, lithium, Li, that's also in group 1, so that's going to lose 1 electron and become a plus charge. Bromine is in group 7A, or group 17, right? Bromine, Br, is going to want to pick up 1 electron, Br minus. So this is an easy one. It's 1 plus and 1 minus, so that's going to just form a 1-to-1 ratio to give us net zero. We would call this lithium bromide. Aluminum and oxygen, I think we just did that on the slide above, so we don't need to do that one again. All right, just to remind you, that's going to be Al2O3, because the aluminum was a 3 plus and the oxygen was a 2 minus. And this would be called aluminum oxide. How about barium and fluorine? Well, barium, you look at the periodic table, barium is Ba, and you find Ba on the periodic table. It's all the way down at atomic number 56 in group 2. So barium, being in group 2, will tend to lose 2 electrons and have 2 positive charges on it. Fluorine, just like bromine and just like chlorine, comes from group 7A or group 17. These are all halogens. So fluorine, F, is going to tend to pick up 1 electron. Right? It'll have a 1 minus charge. Now, at this point, you can probably do it in your head and figure out that to get that to be net zero, you would have, for every 1 barium, you would have 2 fluorines. And we would call this barium fluoride. Now, some of you may have noticed already that bromine turned into bromide. Oxygen turned into oxide. Fluorine turned into fluoride. All right. So there's a reason for that, and it has to do with the nomenclature rules. So when you're naming an ionic compound, right, remember that the cation is listed first, and you use the element name. The anion is listed second, and for the anion, you just use the stem and replace the suffix with a new suffix that is ending in IDE. Now, if you wanted to talk about these ions separately, you would refer to, for example, this as the sodium ion, and this you would refer to now as the chloride ion. All right, so the cation, it's the same element, you just put ion at the end of it. So the sodium ion, the lithium ion, the aluminum ion. Now, notice that you don't need to specify the charge state when you say this. You don't say the aluminum 3 plus ion, you just say aluminum ion. And you know that if it's a main group element, or what we all sometimes call the representative elements, there's only one ionic form for each one. So if it's the aluminum ion, it's only +3 or 3+. If it's the sodium ion, it must be 1+. If it's a calcium ion, it must be 2+. If it's an oxygen ion, it must be 2-. But the name would then be calcium oxide, as the example keeps going. Okay, so it's pretty straightforward then when you're using these main group or representative elements to do this. There's only one ionic form. It's unambiguous. You don't need to specify the number of charges. You just call it the name. So calcium oxide. That doesn't tell you that there's one calcium and one oxygen. You can figure that out from the charge states. For sodium oxide, right, in its name, it's not telling you that there's 2 sodium ions for every oxygen ion or oxide ion, right? That's not in the name, but you can tell that from the fact that these are main group elements, and you can easily deduce what their charge state will be by looking at the periodic table, right? It's not as easy with the transition elements, with the transition metals. Transition metals, as we'll see on the next slide. And that's because with the transition metals, you can have multiple charge states for a particular transition metal ion. So let me explain that for you now. And there's actually 2 nomenclature systems that are used to describe that. For example, let's take a look at iron. Iron, Fe, can actually take on 2 different forms. It could be a 2+ cation, or it can form a 3+ cation. Copper, for example. Copper can be found as a 1+ cation or a 2+ cation. Now, it's not straightforward just looking at it to know how many different charge states it can form. Now, later on in the class, I'll give you some insight as to how you actually can determine this for some of the transition metals. But for the nomenclature systems, you'll already know that it's either present as a +2 or a +3. And in this case, we use 2 different suffixes, OUS and IC. So OUS suffix is given to the lower number of the 2, and the IC suffix is given to the one with the larger charge state. So if it was a +2 for iron in the compound, then it would be called ferrous chloride, right? And here is the the chemical formula for that, right? 2 chlorine atoms, because each chlorine is a -1, and each iron, in this case, because of the name ending in OUS, we know that the iron has a charge of +2 or 2+. If we called it ferric chloride instead, right, the ferric tells us that the iron cation is actually a 3+. All right, now chloride ion is still a 1-, but now we know that it's going to be a different ratio. Right, it's going to look like this if it's ferric chloride. You can see how a system like this can get very, very confusing quickly, because you need to know how many different charge states there are for a given metal, and then know what they are and know which one is higher than the other one, to know the difference between one that ends in us and one that ends in ic. So I prefer to teach the second nomenclature system, which is a lot more straightforward. This is called the stock name. All right, it's very simple, and we just use Roman numerals. Roman numerals tell us the charge state. All right, so in the example of iron in the +2 charge state, that's simply called iron 2. We know now that that is iron with 2+ charges. Iron 3, all right, is going to be iron in the 3+ charge state. And we get to the same conclusions, but it's much more straightforward to know what the charge state of the ions are, and you don't need to know how many different forms of those ions can be formed and what their number of charges would be to figure out which is the higher one and which is the lower one, and so on. Okay, So all of these that we've been talking about so far fall under the category of monoatomic or monatomic cations and anions. You'll learn part of this nomenclature, you don't put two vowels together. So it would be monoatomic, but when you have the two vowels together, you basically drop the O, drop the first one, and this turns into monatomic. All right. And as the definition tells us at the very bottom, these are simply ions that consist of a single charged atom. So that's very straightforward. And this table pretty much summarizes for you many of the ones that are in the main group elements and what charge state they form when they become an ion and what is the name of that ion. Now, I make a point of this because there's also something that we call polyatomic ions, right? As the name implies, they have many atoms, poly, not just one. And it turns out these are held together by covalent bonds. We haven't talked about those yet. Now, normally, something that's held together by covalent bonds, we would just call that a covalent compound. It's a molecule. But this one is a very special kind of covalently bonded molecule that it has an overall, it has a net positive or negative charge, meaning that the number of electrons don't match the number of protons. But now it's not just the number of protons in an atom, it's of all the atoms that are covalently bonded together, right? This is due to a different number of electrons versus protons. These are protons in the compound now, not just the atom. But the rules are still the same, meaning that you have a cation paired with an anion plus an anion, and they have to form ratios that give you a net neutral formula unit. The only difference is that they're not just single atom monatomic ions, they're now polyatomic ions. So for example, you take a look at NH4+, the ammonium ion. NH4+ has a single plus charge, right? We can combine that with the chloride ion, and we would make what we call ammonium chloride. We could take our sodium ion that we've already looked at and combine that with the sulfate ion, polyatomic ion, right? That would be SO4 2-. Now take a closer look at this sulfate ion. That sulfate ion is a covalently bonded molecule. It's a covalently bonded sulfur with 4 oxygens, but overall it has a net 2- charge. So it is a polyatomic ion. Now later on in the class, when we start drawing Lewis structures of these, you'll see how these charges come about. We'll take a look at that later. Right? But this is the sulfate ion, and it has an overall 2- charge. So following the same rules that we did earlier, you need to mix these in ratios that give you net neutral. So that would give us Na2 SO4, and you would write it this way. Once you write the compound, you don't include the charges. Let's make a note of that. You don't include the charges in the formula unit. So once again, you need to either recognize what they are from knowing what they are from the periodic table, especially if they're main group elements, or in the case of when it's a polyatomic ion, sulfate, you kind of just need to know what they are. And we would call this compound sodium sulfate. All right, now let's take a closer look at some of these rules for compounds containing polyatomic ions. The rules are really the same as before, except now we have polyatomics to consider as well. So just as before, we need to predict the charge state if there are monoatomic ions present. And then we need to obtain the formula and the charge state for the polyatomic ion, and you would either have to memorize them from using them over and over again, look them up in a table if the table is provided like this, or they would be provided for you on an exam. And then, as before, you want the combination, the ratio of the cations and the anions to be such that in the compound they are net zero in the end. Now in this case, you'll sometimes need to use a parenthesis. And let's take a look at what we mean by that. So let's look at magnesium phosphate. So following these rules, magnesium, we can use the rules that we did before, look up where magnesium is on the periodic table, and we recognize that if it can form an ion, it will lose two electrons and become a 2+ charged cation. The phosphate is a polyatomic ion. It's a polyatomic anion. We look that up in the table, or you will just know it, that it's PO4 with an overall charge of 3-. So just as before, we need the ratio to be such that this forms a net neutral compound. We can do it either by the lowest common multiple or the crisscross method. If we use the lowest common multiple, we know that we need to have 2 times 3 equals 6 charges of each. So to get 6 plus charges, we need to have 3 times the magnesium ions, and to balance that with 6 minus charges, we need 2 times the number of phosphate ions, because each one of those is a 3- charge. If you want to do it the crisscross method, you would write magnesium, the cation is always first, the anion is always second, PO4, and since we know that the magnesium ion is normally a 2+ and the phosphate is normally 3-, and you take the number of charges of one and that becomes the subscript of the other. So that's the crisscross. Now in this case, we can't just write PO4 sub 2. We need a parenthesis. You put a parenthesis around the polyatomic ion and you show then with the subscript 2 that there are 2 units of that polyatomic ion. Now let's just go through some more examples, and you can pause the video and write these down and try to answer these yourself if you want. So on the left-hand side, let's just name these compounds. We recognize this is NH4, that's an ammonium ion. I think we did this one already, or something similar to it. This is ammonium chloride. I think we did do these already. Well, I'll just write them down again. Barium sulfate. Again, it's the sulfate ion here. Now here's a case, Fe and then NO3 in parentheses sub 3. So we need to recognize that this is the nitrate ion, and there happen to be 3 of them. Now we don't need to specify that in the name, but we know by looking up on the table that the nitrate ion, NO3, is associated with a single negative charge. Looking at the formula, we now know that there are 3 negative charges associated with the anion component of this compound, which means the cation component, which is iron needs to be in the +3 charge state for that to be net neutral. So we would write this as iron 3 nitrate. So you can actually tell what the charge state of the iron is by looking at the number of anions associated with it. Look on the table. This polyatomic ion is called the bicarbonate ion, and I'll talk more about the naming of those in a little bit at the very end. All right, and here we have the copper ion. Now, do we need to specify the charge state of the copper? Yes, we do. So what's the charge state of the bicarbonate ion? You know that from the table that has a 1- charge on it. So this would be copper 1 bicarbonate. This compound's a little easier to name. We recognize that this is the hydroxide polyatomic ion. We know from the table that the hydroxide ion has a 1- charge. The formula is already written for us. Calcium can really only be in one charge state. It's a main group or representative element. So if it can form an ion, it will form a +2 charged cation. And so we see with using the parentheses that there are now 2 hydroxide polyatomic ions associated for every single calcium cation. Right? This one is simply named calcium hydroxide. Now let's practice working from the names and deriving what the formula is. Aluminum hydroxide. Remember, cation is always listed first and the anion is always listed second. Aluminum ion, well, we look at the periodic table, you see where aluminum is in group 3. It has a valence of 3. If it can, it will lose 3 electrons to come up with the electron configuration of the nearest noble gas. That's the most stable. So aluminum, if it can, would lose 3 electrons and become 3 plus. The hydroxide ion, we know, again from the table, I'll just put it here, is each one has a single minus charge. So you can do the crisscross method, or you can just look at it. You do these long enough and you can look at it and recognize that for every aluminum we're going to have 3 hydroxide polyatomic ions for that to be net neutral. And we would write it like this. Ammonium sulfide. Now ammonium, that's the ammonium ion, NH4, right? That's normally singly charged. Now this is sulfide, not sulfate and not sulfite, but sulfide. Right? That means it's simply sulfur that's formed an anion. It's picked up 2 electrons. Again, in doing so, it becomes isoelectronic with its nearest noble gas and therefore being in the most stable electron configuration. So we have 2 minus charges and 1 plus charge. So again, we need to use our parentheses. In this case, they need to be around the ammonium ion to show that we have 2 of those for every 1 sulfide ion. Again, to give us a compound that is net neutral, a formula unit that is net neutral. Calcium nitrate. Well, calcium normally forms a +2 charge. It's a main group element. Nitrate, the nitrate ion, NO3, has a negative charge associated with it. So we need to use our parentheses again. For every 1 calcium cation that has 2 plus charges, we're going to need 2 nitrates because each one of those has a 1 minus charge. So that gives us a balanced formula unit, a net neutral formula unit. Chromium 2. Now we know the charge state of the chromium ion. It's a +2. The sulfate ion is 2 minus. So this one is easy. It's just written without any other subscripts. We have 1 unit of each of the cation and each of the anion. Iron 3 oxide. Again, the Roman numeral is telling us the charge state of the iron. This is a +3. The oxide, oxygen oxide, it's picked up 2 electrons to become its anion. And by common lowest common multiple, that would be 6, like we showed before. Or by doing the crisscross method, you can show that in the formula, the unit that's net neutral would have 2 iron 3 ions and 3 oxide ions. All right, so that was all about ionic compounds. Let's talk a little bit about covalent compounds. When you form covalent compounds, they usually form from reactions between nonmetals and or between atoms that have similar electronegativity, and we'll be talking about electronegativity soon as well. Now, unlike the ionic compounds that exist in formula units that are in much larger arrays, a covalent compound exists as a discrete molecule. So when we write the names, we need to be specific about, once again, how many atoms of each element are involved, and that's because sometimes it can be a different number of atoms depending on what the compound is, even though it's between the same 2 elements. For example, take a look at CO2 and CO. These are both compounds that have carbon and oxygen in them, but there's a different number of atoms depending on what the element is, or depending on what the molecule is. So we have a different naming scheme for that. So before I tell you the names of those, let's look at what the rules are for naming covalent compounds. So firstly, we write the name of the elements in the order that they appear in the chemical formula, and then we use the appropriate prefix to indicate the number of atoms. And we use these prefixes to designate mono for 1, di for 2, tri for 3, and then you just have to learn these: tetra for 4, penta, hexa, hepta, octa, nona, and deca for the different number of atoms. So following those rules, let's look at CO2, We all know that this is carbon dioxide, but let's follow the rules. First we write down the chemicals in the order that they're written. So carbon, and now oxygen is going to be next, but we need to use the prefix di because there's two of them. So it's carbon di, and then before I finish writing oxygen, I need to look at the second rule. For the last element, you use the stem name plus the IDE suffix, just like we did with the ionic compounds. So this would be dioxide, right? And that's different from CO. They're both compounds that contain carbon and oxygen, but they're in different ratios, and they are different covalent molecules. And we'll be looking at the structure of those later on in the next chapter or two. So following the naming protocol, it's still carbon, and it's not dioxide, but we need to specify that there's one oxygen, not two or not three, and so on. So this would be monoxide. And the other little bit to add with the naming here is when you have it, when you have two vowels together, you drop one. So in this case, we drop the O, and this would just be monoxide, carbon monoxide. All right, let's look at this one up here. All right, we start with carbon, and we have 4 fluorines, but we end in IDE, and the prefix for 4 is tetra, so this would be carbon tetrafluoride. Right, this one we start with nitrogen, but there's 2 of them, so it's dinitrogen, and then not tetraoxide, right, but tetroxide. So really, I dropped the wrong O. I had to choose one or the other. All right, you dropped the first one. All right, so in this case, in tetra, we dropped the A and just went right to tetroxide, dinitrogen tetroxide. Okay, so now let's work backwards. Let's use the prefixes in these names to figure out what the ratio of atoms are in the molecule. These should be pretty straightforward. So nitrogen trichloride, right? Nitrogen trichloride. There, we're done. There's 3 chlorines. Diphosphorus pentoxide. So we know that there's a phosphorus, and we know that there's oxygen, and there are 2 phosphorus atoms, and there are 5 oxygen atoms. Now there's nothing else here to figure out. You don't have charge states to work with because these are not ionic compounds. These are covalent compounds, so all you have to work with to know how many there are is by looking at the prefixes. Now, for the names, oftentimes we use very common names. For example, we all know that H2O is water, but we could call it dihydrogen monoxide. That's water, right? But we usually use the common name. Like we don't have nitrogen trihydride, we just call it ammonia. Often we'll also use the organic names, and you would learn this if you went on to study organic chemistry, like ethanol or ethyl alcohol. And then here's a common name for a much larger carbohydrate that we all know and love called glucose. So for the common names, there's no other way to know them except to have them memorized, or look them up in a table, or have them provided to you. All right, so for our last subject, we're going to talk a little bit more detail on some of these polyatomic ions that we were discussing earlier. These fall under the category, they're all called oxoanions. And as some of you will see later in this course or in the next course, there's also a naming scheme when these oxoanions are the conjugate base of acids, or what we call oxoacids. So I might talk about those just a little bit here as well. So here is the sulfite ion. If we look this up on the table. The sulfite ion, this is the sulfate ion. So in a similar way that I talked about earlier with the monoatomic ions, when you had multiple charge states, we had different suffixes. We had the ik and the us to designate whether it was the higher charge state and the lower charge state. Fortunately, in that case, we also have the Roman numeral system, which is much easier to follow. We don't have that luxury here in naming the oxoanions. So now we're going back to looking at the number of oxygen atoms that are present in the polyatomic ion. So this is based on number of oxygens, right? The lower number, you end in the suffix "ite," and the higher number, you end in the suffix "ate." And so in this case, it does presuppose that you know what all the different forms are. Same is true with NO2 and NO3 polyatomic ions. This would be the nitrite ion, and this is the nitrate ion. Now, in some cases, there's only one form with the number of oxygens, like in CO3, that's called the carbonate ion. Now, you still need to know what the charges are, and once again, when we get into drawing the Lewis structures of some of these, you'll see where the charges come from. We know that the carbonate ion is associated with a 2- charge, and oftentimes they will be associated with hydrogens as well. Formally, in this case, when we stick one hydrogen on it, we're also removing one of the charges, right? And formally, we would call this the hydrogen carbonate ion. But there is also an older naming scheme for some of these that we actually cling to, and I use it all the time. I think everyone uses it all the time. You very rarely see this written as the hydrogen carbonate ion. If you look up on that table, you'll find that it's called the bicarbonate ion. Let's switch to another color for these last ones. So once again, on the table, you'll look up, there's a phosphate ion that we know has 3- charges. And just as I explained for carbonate, you could, we don't have other names for the phosphate ions, but you would have hydrogen, phosphate ion, or dihydrogen, because now there's 2 phosphate ions, all right? You can have 4, and you see this with the halides, or with the halogens. So with the halogens, especially chlorine and bromine, you can have up to 4. So here we have to invent 2 additional terms. We're still going to have the ite and the ate, and we're going to use those for the 2 in the middle. So this would be the chlorite ion. This would be the chlorate ion. And if you go beyond chlorate, to go from 3 to 4, that would be hyperchlorate ion. And if you go below 2, you would be hypochlorite ion. Now, when you go on to later subjects in chemistry, you'll be doing some acid-base chemistry, and oftentimes you'll be using these oxoanions as the conjugate base in these acids. One that you're probably very familiar with uses the sulfate ion in the acid. If you have an acid like this, the sulfate as an acid turns into sulfuric acid. That would be H2SO4. If it's the ite, right, from SO3, then the naming for that as an acid will be sulfurous acid. So again, the prefixes now, we're back to this ic and us for the suffixes. All right, for the nitrates, the acids are called nitric acid, again ending in the IC for the higher one, for the 8, and the ite turns into nitrous acid. Now for CO3, it's there's only one, so this would form carbonic acid. When you start doing them with some of these, so with the phosphate, this would be phosphoric acid. Again, there's only one to choose from, so we only have the one suffix, ic. And then finally, when you get to ones like with the halogens, we have 4 choices. Forming the acids with any of these, this would be hypochlorous, because the us is associated with the ite, but we just have a hypo in front of it, right? This would just be chlorous acid. This would turn into chloric acid. And in this case, it's not hyperchloric, but it would be perchloric acid. And that should about do it.